This video, we're going to review integrals that we've seen before. You guys have been working with integrals when you've been doing your volumes of revolution. And then we're going to look at a couple new methods. Okay, so we'll start with the real basics and work our way up. So one way we can integrate is just by knowing the derivative, right? So the antiderivative of the cosine function is the sine function. We just know that that's the derivative, right? Basic function. I could also do this from as a definite integral, which you've been doing with your volumes of revolution. So it would be sine evaluated from 0 to pi over 2, right? And then we plug in pi over 2. We plug in, fundamental theorem of calculus. We subtract sine 0, and we're on our way. The area under that curve from 0 to pi over 2 will be equal to 1. Okay, then we got into u substitution. So u substitution, you look at this thing and you say, well, what am I going to let u equal? Most of the time our choice for u was the input to the composite function. So in this case, that's the exponent. So we let u equal 4y squared minus y. And then we did the following work. Du would be 8y minus 1 dy. And then the way I do these, a couple different ways to do it, is to solve for dy so we can sub it out. And dy would be du over 8y minus 1. And then I do all the substitution. So I got the 3, the 8y minus 1, e to the u. I sub in dy with what it's equal to. And most of the time we get some cancellation. They're set up nicely that our original independent variable would go away. And then from there, I'll go this way. I integrate 3e to the u, which is 3e to the u, plus c. And then I back substitute, and I say 3e to the 4y squared minus y plus c, and that would be my answer. And I can always check that answer if I want by integrating it. Right? If I take the derivative of that, I should get this. All right, and then the next step would be to deal with a definite integral with u substitution. So in this case, I let u equal 1 minus 4t cubed. Du is negative 12t squared. Dt is du over negative 12t squared. In addition to that, if I'm changing my variable, I got to change these bounds. Okay, so I would do it like this when t is negative 2, u is, and I plug it into u up here, 1 minus 4 times negative 2 cubed, which is equal to 1. This is going to be negative 8. Negative 8 times negative 4, 32, so that should be 32. And then I say when t equals 0, u is 1. Okay, so when t equals negative 2, I got 33. So I'm changing my bounds here, 33. When t equals 0, u is 1. And then I have 2t squared, square root of u, dt, which is this thing, du, over negative 12t squared. Then I clean it up. 2 over negative 12 is negative 1/6. 33 to 1. Square root of u, du. Okay, and I'm done with these bounds. I don't have to worry about them anymore because I just changed them. I changed everything over to u. Now this looks a little funny to me. I usually don't like to, you can work with it like this, but I usually don't like to leave it here. That is, my lower bound is bigger than my upper bound. So we have a property where you can switch your bounds, and it changes your sign of your integral. And then square root of u is u to 1/2. And then I'm saying u to the 3/2 times 2/3, evaluated from 1 to 33. And I just plug it into u directly. So that's going to give me 2/3, 33 to the 3/2, minus 1 to the 3/2. And I just forgot my 1/6 here, so I'll bring that down. and then I'll be done. 1/6 times 2/3 should give me 1/9. Okay, so now let's move on to new methods. So if I look at this, these three integrals here, they look very similar. Okay, one of them you know how to do. It should be straightforward with u substitution, even though they all look very similar, right? Of course, this one has, it's all about the denominators are the same. This one has an x squared in the denominator. I'm sorry, this one has x squared in the numerator. This one has x in the numerator. This one has a constant. So how do we deal with these? Well, this is the one we already know how to do. So let's start with b. I said you usually let u be the input of your composite function, but in this case, we let u be the denominator. You might remember these. We get a natural log function if it works out. That is, we're integrating, the rule here is u prime over u du is just equal to u. Okay, so, I'm sorry, natural log of u. That's what we're going for here. So let's see if that works out. So du is 2x dx, and dx would be du over 2x. So I do my substitution for b, and it's 4x over u times dx, which is du over 2x, and there's my cancellation, just like the previous problems. So I end up with 1 over u du, and I get 4 times the natural log of u plus c, and then I can do my back substitution, x squared plus 9, easy. Okay, now for the harder ones, look at a. So a is new to us. We started the semester with taking the derivatives of inverse trig, so now we got to go the other way. So these should look familiar. Okay, so we might have done, so like your derivative for your arctangent of x is 1 over 1 plus x squared. That looks kind of like this one. Okay, but with a little bit of substitution, we can do a little bit better. That is, if we're trying to integrate not just 1 plus x squared, but something squared, a number squared, plus a function of x squared, this is like the chain rule or the u substitution equivalent, then we can use these formulas. Okay, so that's what we're going to lean on if we can. Instead of, we can still do our u substitution. I'll show you a bunch of examples after this one. But we can also just try and do this with our formulation. Okay, we'll do it both ways. So for example, if I see this guy, if I see a, and I have like an x squared plus a number squared on the bottom, then I say to myself, that's got to be arctangent. All right, and I can use this formula. So do I have this formula here? Like, how do I use this thing? Well, what's a squared and what's u squared? You could just use your formula and say, well, u is x, and a is the constant, right? So what's a? A is 9. And then I don't have to worry too much about how it works out if I'm relying on the formula. And then I know that the answer is, well, you can pull the 4 out. And then I say, okay, does this fit the pattern? Does the derivative of u, so it's a little confusing, right? U is what's being squared. So we're so used to having like a 2x up here, and then up here is the derivative of the whole input u, which was our whole denominator. That's what we're used to with like these ones. Okay, but now you gotta be careful. Use the guy being squared. So this would also work. We could do some more complicated ones later, right? But if I had like 4x to the 4th plus 9 and like an x squared up here, this would work, because what I would do is call u is what's being squared, right? So u equals 2x. And this wouldn't work by the natural log way, because I can't let u for u substitution be this whole thing, because this would have to be the derivative of the denominator. So this would also be an arctangent guy. So you got to look out for that. It's a lot of pattern recognition. This is an arctangent integral because if I isolate u, something that's being squared, the variable that's being squared, then this is the derivative of that living up here, just like my formula says. Okay, so we'll get some more practice with that. That's our new method. That's our new method number 1, identifying these inverse trig functions. Okay, so how do I finish off A? So it's going to be 4 times, and then I use this formula. What's 1 over A? Oh, I got A wrong. You might have been thinking, well, A isn't 9, A is 3, right? It's the number that's squared, the number that's being squared, or the square root of that number if you want. So it's 1 over 3 arctan, which usually I write like this, and then u over A plus C. Okay, and the only way I can clean that up is multiply 4 times a third, which is 4/3. So I would need that parenthesis, and I have a nice answer. And if you want, since you are practiced with taking derivative of inverse trig function, if you take the derivative of this thing, remember we can always check that. Take the derivative of this thing, then we should get that as our answer. Okay? For any of these, anytime you take the derivative of your integral, you should be able to get your derivative or your original integrand. All right, one more. This is another new method for us, but it's an algebraic method. And then from there, we'll be able to do other methods that we learned. So when you have, if you tried all your things, all your methods, you say, well, wait a minute, my new method is trying to match this to one of my inverse trig. That's not going to work because I don't have anything that fits that pattern. Arctangent's the closest, but that's not going to work. I can't let u be x squared plus 9 because when I take the derivative of that, I would need this to show up in the bottom or the numerator. Just 2x would have to be up here, and it's not. It's 4x squared or an x squared term, so that's not going to work. So there's a step we can do. Anytime the degree, I'll write it down, if degree of denominator is greater than degree of numerator, and I have to adjust that greater than or equal to, do long division. Okay, so we can rewrite this integral as the quotient and the result. All right, so do some long division, some quick math review. You're dividing that into this, and there's no x term, there's no number term, so what we do is a 0x term and a 0 number term. We say, how many times does x squared go into 4x squared? The answer is 4, so I put it in the constant term, and then I multiply 4 by that. So 4x squared, there's no x term, plus 0x plus 4 times 9 is 36. Right, so I just multiplied the 4 by this guy. And then I subtract, remember doing this? Gone, gone, remainder 36. Okay, so this integrand then can be written as quotient plus the remainder, sorry I had to think about that for a second, the remainder over the divisor. Okay, so this is in fact the same thing as this. If you got a common denominator, added these together, you get the same thing. An easier way to think about this for long division, what's like 16 over 5? It's, how many times is 5 going to 16? 3. Right? How many times is x squared plus 9 going to this? 4. Plus, what's left over? The remainder would be 1 over what you're dividing by. Same idea here. All right, and now we can integrate. So I integrate that. The 4 is 4x. This we just did, so pull out the minus 36. And I believe we just did 1 over x squared plus 9 because we got, just for the 1 over x squared part, we got 1/3 arctangent before we multiply by 4. 1/3 arctangent of x over 3. 1/3 arctangent of x over 3 plus c, and then we can simplify. 4x minus 12 arctangent of x over 3. Okay, so new methods. If this degree is equal to or less than this degree, long division. And then look out for our new inverse trig functions.